All right, moving on. We are still in 6.1. Believe it or not, I know this is the third video, and there's still going to be a few more. It's just a big section. So the next thing that we need to talk about, we're still finding volumes, but now we're not finding volumes using that method of slicing with the cross-sectional areas. Now we're going to be finding volumes using revolution. So if you just think about some kind of space, some kind of area, a flat area. If you take that area and you revolve it around either the x-axis or a y-axis, you're going to generate some kind of three-dimensional shape. So let me go over to Desmos here, just to kind of to show you what I mean, because this is the first question that we're going to do here. So let's say we have this graph. This is the graph of square root x, and it's only going from 0 to 4. So just the square root x graph from 0 to 4. Think about cutting it off here at 4, and then the area that we end up with underneath the function to the x-axis. If I were to take that and then revolve that area around the x-axis, I would generate a three-dimensional shape. It'd be kind of like this big, skinny bowl that we would do here. So just to go over to the book, it would be this shape, right? This is the shape that we're generating by revolving it around the x-axis. Now, I don't just have to revolve it around the x-axis. We could revolve it around the y-axis, and we end up with this weird donut-looking thing. It doesn't even have to be the x or the y-axis. We could revolve it around any horizontal or vertical axis to generate some kind of three-dimensional solid of revolution. Let's talk about finding the volume of the solid. So, if we were to go back to the method of slicing, if this was a three-dimensional solid by revolving it around the x-axis, then every single slice is going to be a disk or a circle with a little bit of a height to it. We can find the volume of those using a simple formula. So let me get back to the book here. So here we have our disk that we're generating, and every single disk has the same volume to it. So this is what we call the disk method. The disk method is used for finding volumes of solids of revolution. Okay. The way we're going to do this is kind of using method of slicing, but it's always the same thing. So the cross-sectional areas are always circles or disks, I guess. We'll just keep it with disks. Where the formula of that, which is the formula for the volume of a disk, is going to be pi, and then whatever the radius is at that particular location, we'll use a capital R. Whatever that radius is, squared. So just pi r squared to get the area of the disk at the location x. But it's going to change as we move. So this radius of x, going back to the graph that I was dealing with here, as I move across the x-axis, the radius is just the distance from the x-axis to the function itself. So if I'm at location x, then I'm really looking for the y value here. And I get the y value by plugging that x back into the function. So if I'm at 3, then this y value here, which would be the radius of the disk, would just be square root 3. Okay, so let's go ahead and answer this question then. So just to write it all out, we're going to find the volume of the solid generated by revolving the area under the square root graph on the interval 0 to 4. Around the x-axis. Okay, so find the volume of the solid generated by revolving the area under the square root x graph on the interval 0 to 4 around the x-axis. So again, going back to Desmos, that's this area that we're revolving around. All you have to do is use this as your cross-sectional area. So you can kind of think of it as like a generic volume that we're always going to have for the disk method. The volume is always, not just for this question, but always whatever your interval is, a to b, over that pi, the radius as a function of x, quantity squared dx. This is on that formula sheet that's in Moodle, so you can just kind of look at it there if you have a question like this. And just plugging in this particular question, the volume is going to be the integral. This is going from 0 to 4. pi. My radius as a function of x is my function square root x, and it's going to be that thing squared. So that is just going to cancel out. We're going to have the integral from 0 to 4. We still have the pi, and then the square root of x squared is just x dx. This would have antiderivative of pi over 2 x squared. And then we're going to evaluate that between 0 and 4. So if I plug 4 into this, 4 squared is 16, divided by 2 is 8 pi, minus plugging 0 into that is just 0, so we just get 8 pi as our final answer. So this shape that we have, and I'm going to go back to the book here, this shape has a volume of 8 pi cubic units. Okay, so that was a pretty quick one. So just to do one more, I think this one's pretty fun. Let's do this next one. So now let's find the volume of the solid by revolving the circle. So this is just a generic circle, x squared plus y squared equals a squared. So it's a circle of radius a at the origin, and we're going to revolve that circle around, let's just do the x-axis. It doesn't matter which one we revolve it around because it's the same thing. So again, in Desmos here, I graphed a circle for us. I just graphed a circle of radius 2, although I did make a little slider here so we can move it all around to be fancy. So let's say if we did have a circle of radius 2 and we're going to revolve that around the x-axis. Revolving this around the x-axis is actually going to make us a sphere. So really what we're doing is we're finding the volume of a sphere by just using this area and revolving it around the x-axis. One thing that we can do to get kind of clever is that we don't have to go from -2 all the way to +2. We could just go from 0 to 2, but then double the volume that we get to get both sides of the sphere. I think I'm just going to go from -2 to +2 though, just to be fancy. So what we need is that if we are from -2 to +2, we have a generic value x that we could be located anywhere. So let's just say maybe my x is here. Oh, I can get the drawings. I'm going to get a little bit better of a color here. Let's go back to red, I guess. So let's say that this happens to be the location of my value x at this particular time, whatever it means. At this value, if I'm talking about the disk that I'm creating around the x-axis, this is going to kind of be my disk, right? It generates this circle, where the radius of this circle is the height from the x-axis up to the top edge of this circle. This would be if I knew the location x and I plugged it in, it's the y value, which is the height of this radius. So going back to the book here, not the book, sorry, going back to the notes, we're going to take this and we're going to solve it for y. So solving this for y, we're going to subtract the x squared over, and then we're going to take the square root. Again, I'm not going to worry about the positive and the negative because I only want the positive part of the radius, going back, I only want the positive y value. I don't care about the negative y value from that square root because this is going to be the radius of the disk that we create. Okay, so now we're ready to find the volume here. So the volume is going to be, again, coming from the formula up top here for the disk method, the volume is just the integral from a to b, and here I need to be a little bit more careful thinking about it. So going back to the graph here, I can't go from -2 to 2, because remember that was just a placeholder that I put. Really, it should be this variable a. So I should be going from -a to +a. Now you still could do that trick where you go from 0 to a with a 2 out in front if you really want to. So my integral values, my limits are -a to +a for a generic circle. Then it's going to be the integral of pi, the radius, which is the square root of a squared minus x squared, that whole radius squared. Okay, same thing's going to happen as before. As I do this integral, the square root and the squared are going to cancel each other out. So we end up with a pi and then just a squared minus x squared. Just to do this one pretty quick, you want to do the antiderivative of each of these separately. So I'm going to distribute the pi and then do the antiderivative. So for the first one, that's really a squared and a pi. Those are both constants. So we're just going to have the a squared, the pi, and we're going to throw an x on that. For this one, again, there's a pi out in front. So the x squared is going to change into 1/3 x cubed. Now this whole thing we're evaluating from -a to +a. If I plug positive a into this, it's going to add another a onto this first term, and I'm going to end up with pi and then a cubed, minus, if I plug a positive a into this x cubed, I'm going to end up with the pi, the a cubed over 3. So that was plugging positive a in, minus, now we're going to plug negative a in. If I plug negative a into here, I'm going to get negative pi a cubed. If I plug negative a into this one, negative a cubed is still negative, so that cancels out to make that a positive pi over 3a cubed. Okay, here we have a pi a cubed and another positive pi a cubed, so those will add together to be 2. I'll write it as a cubed pi. Here we have a negative pi a cubed over 3 and another negative a cubed pi over 3. So those will combine together to be a negative 2 a cubed pi over 3. Now we can combine these together. So if I put this first one as a fraction over 3, I'll come down to the next line here. To make this a fraction over 3, I'd have to change that to be 6 a cubed pi over 3 minus the 2a cubed pi over 3. And now that they're like fractions, we can just subtract the numerators. 6 minus 2 is 4 a cubed pi over 3. And I think that's right now. So if I go and I just go to Google here, and I Google the volume of a sphere. Yeah, right. So the 4/3, the pi, and then the radius cubed. So going back to our answer, the 4/3, the pi, and then the radius cubed. So yay, all right, the disk method really does work, even for these generic questions where we're just trying to find the volume of a sphere.